Well, welcome back to another session. I want today to talk about something very important. We talked about voltage, we talked about current, we talked about resistance. We understand from the last lecture that voltage is a separation of charge. Anything that produces a voltage, what that thing is doing is separating charge, creating an electrical potential difference. We call that electrical potential difference voltage. So voltage is a separation of charge. Current is charge in motion. It takes a voltage to cause a current, and resistance is the opposition to current flow. Today what I want to do is talk about how are these things related? How is voltage, current, and resistance related? In addition to that, I want to talk about a concept called power, and we'll finish up talking about efficiency. So that's the topic for this week. If you haven't sent me your text, please go ahead and text the number you see on the board. In the text, put your first name and last name, and also write EET 131. Our attendance is due today, so what I do is I go and I look at the text you sent me. If you don't sign in quotes, if you don't sign in within the first 2 weeks of class, then you're removed from the class. So you want to make sure that you've been taking attendance in all your classes and that there's a record of you showing up for the first 2 weeks. I actually already reported that, so hopefully everybody's been signing in over the last couple of sessions. And if I think everybody is marked, I think I might have been 1 or 2 people that didn't show up in my sign-in. So those people are actually here. You will not be on the roster after this week. But I think the people that are online now, I think you guys are okay. So go ahead and send me the text. And I want to talk about voltage, current, and resistance. How are they related? And I'm going to start by this. In physics, there's a general rule or principle that says effect equals cause over opposition. Effect equals cause over opposition. And this is a really general relationship that you can use this to talk about a lot of effects that you might want to establish. For example, let's say that the effect you want to establish is acceleration. You want to make something speed up, go faster and faster and faster. So the effect is acceleration. Does anybody know the cause of acceleration? What causes something to speed up and go faster and faster and faster?
A force?
A force. Force is the cause of this. Force is the cause of acceleration. And the opposition to the acceleration is called inertia. And in physics, the way we represent inertia is by using something called mass. And so there's this relationship that the physicist Isaac Newton came up with. We use A for acceleration, F for force, and M for mass. And you solve this for F, you get one of Newton's laws, F equals ma, if we were talking about acceleration. Well, in electrical engineering, electronics, what we want to make happen, the effect we're trying to establish is not an acceleration. What we're trying to make happen is current. We're trying to make current flow. So the effect we're trying to establish is a current flow. The cause of a current flow is voltage. And the opposition to current flow is electrical friction or resistance. And so this relationship, voltage, resistance, current is voltage over resistance. This relationship has a name. These variables are related in the way that you see here. And the name of this relationship is Ohm's law. And typically when we have these relationships, we don't want to write out words. We use symbols to represent each quantity. And I already mentioned in the last video, the last class, we use I for current. We use a capital V as in Victor or E as in Edward. We use that for voltage. And we use R for resistance. So here is Ohm's law written out as an equation. And this is the fundamental law of electronics. Without this, we can't do anything. The simple relationship, I equals V over R. So you want to make sure you know this equation, this law, and you also want to be able to write it in various forms. So the standard way of writing Ohm's law is as you see it here, I equals V over R. But you should be able to quickly solve this for any equation or any variable. You should know right away that V equals I times R. And you should know right away that R equals V over I. So these are three ways of writing Ohm's law. And this is what you're going to use for the rest of the semester. Now, what's important here, often in engineering and science, is not so much the answer as it is the relationship between the variables. What's the relationship? So let me write something on the board and you tell me what it means. What's the difference between this and this? What's the difference between those two symbols? I got one here and here. What's the difference?
Does one mean infinity?
Oh no, infinity is this. That looks more like a fish sign, so it looks like this. So what does this one mean? Everybody, what does this one mean?
Equal.
So what does that mean? When you say something is equal to something else, what are you saying?
Same quality.
Okay, the same quantity, same value, the same something, right?
Yeah.
You know, you can have a dollar bill and you can have 100 pennies. They're different forms, but they have the same value. So something about what's on the left and the right are exactly the same. It can have different forms, but they're exactly the same. Well, over here, I can write a 4, and maybe on this side over here, I can write a 2 plus 2. They're in different forms, but they have the same value. So equal means same. Something about them is the same. What is this? In math, what do they call this? That's the sign of what? You guys never seen that before, that symbol? That's called the sign of proportionality. If you've never seen it before, please write it down. The sign of proportionality. So whereas here, this says A is equal to B, this says A is proportional to B. A is proportional to B. When I say A is equal to B, I'm saying something about the two quantities is the same. They may have different forms, but there's some part of the quantities that's equal. They're the same. But what does it mean when I say A is directly proportional to B? What does that mean?
It's dependent on B.
Okay, in what way? It is dependent on B. In what way? Well, here's how it's dependent. If I increase B, then A is going to increase. If I decrease B, then A is going to decrease. If I double B, then A is going to double. If I cut B in half, then A is going to follow its cut in half. Whatever I do to B, A is going to follow in the same way. And so I can say that A is directly proportional to B. Now, how do you know when two quantities are directly proportional? The way you know it is by looking at the equation. If both quantities on the left and right side of the equal sign, if they're both in the numerator, or if they're both in the denominator, then we say that they're directly related or directly proportional. So in this equation right here, if I write this left side as a fraction, I see that I and V are both in the numerator. That means I can write I is directly proportional to V. And so the relationship between I and V is a direct relationship. Remember the first day of class, the very first thing we started off talking about in this class was that math is the language of science and engineering. And I also said that when you look at an equation, never look at an equation as just the way to get an answer. An equation really is God's way of allowing us to speak to nature. That's not mine. Rene Descartes said that. It's God's way of allowing us to speak to nature. We live in a mathematical universe. And so what's important is what the equation is saying. And one way to tell that is by looking at the relationship between variables. I is directly proportional to V. Now, it's not enough just to say, all right, I get that. It's directly proportional. It's got to make sense to you. Everything we do in that class, there's the math sense and there's your gut feeling sense. Does that really make sense? So the math sense, everybody can see this. You're shaking your head right now. Yeah, I get that. But does it make sense to you in your gut? If voltage is the force to make electrons move, if voltage causes current, does it make sense that if I increase the voltage, if I increase the force that makes the electrons move, does it make sense to you that I should get more current? Does it make sense that if I decrease that force, if I decrease the voltage, I'll get less current? If I double the voltage, I'm going to get twice as much current. If I cut that voltage in half, I get half the current. Whatever I do to V, I follows. V and I are directly proportional. Do you see it?
Yeah.
Okay, that's important. I could write this another way though. Look, I can do this. Instead of writing A is directly proportional to B, what if I do this? What if I say that A is directly proportional, not to B, but to 1 over B? And what does that mean? What does that mean?
If you raise B, A lowers.
Exactly. He said if you raise if you raise B, A is going to lower. If I lower B, A is going to raise. Whenever I do the one, the opposite happens to the other. If I double B, and I cut A in half, if I cut B in half, I double A. I say that A is inversely proportional to B. A is inversely proportional to B. Now, how do you know in an equation when two quantities are inversely proportional? Well, if that's the case, then one quantity will be in the numerator and the other one will be in the denominator. And I see that I is in the numerator when R is in the denominator. So if I wanted to, what I can write is this. I can write I is directly proportional to 1 over R. I can say I is directly proportional to 1 over R. I can just say I is inversely proportional to R. And everybody sees that, you shake your head, you say, yeah, okay, I get that. That's not too bad. But that's not enough. It's got to make sense in your gut. Does it physically make sense to you that if I increase the resistance, if I make it harder for current to flow through a material, then less current can get through? If I increase the resistance, the current should decrease. If I lessen the resistance, I should get more current going through. If I double the amount of resistance, I make it twice as hard for current to go through, I'm going to get half the current. If I take half the resistance, the current's going to double. Whatever I do to R, I do the opposite to I. The relationship between these variables is very, very important. I and R are inversely related. And what you're going to find out in this class, and by the way, I don't know if I mentioned this or not, your first face-to-face lab will be next Tuesday. So next Tuesday, no online lab. You'll come in. I'll post all this on Blackboard in the next day or two. But you'll come in. You need to make sure you have a mask. Make sure you bring your digital multimeter with you, and there'll be some stuff. Some of the stuff to turn in you've already uploaded, like the universal assignment. Anything that had a link for you to click on, you upload it. But anything else like the homework 1, there was a supplementary quiz, all that stuff you're gonna actually bring in the hard copy to me on Tuesday. But on Tuesday, one of the things we're gonna talk about when you meet for lab is what really is electronics. Electronics has a meaning. And what we mean when we say electronics is really simple. All we mean by electronics is the controlling of current. In electronics, we control current. What is current? Current is the flow of electrons. And you can see from this relationship, this equation, there's only two ways to control current. I can control current by varying the voltage, and I can control current by varying the resistance. And most often, we have a fixed voltage. So we can't adjust that. When you buy a battery and put it in your car, it's 12 volts. You can't adjust that. When you put a battery or cell in your device, you can't adjust. The voltage is fixed. So often this is not an option. So if I'm going to control current, and I can only control current by changing voltage or resistance, then more often than not, the way we're going to control current is by varying resistance. So this is important. Simple idea, but important. I think on Tuesday, when we talk about resistance, we got a whole lecture on resistance. Color coding and resistive devices, it'll probably just blow your mind. You'll see exactly how this is done. But it all starts right here, the fact that there's an inverse relationship between I and R. So here's what I want to do now. Last week, we spent all week talking about physics. There wasn't no electrical engineering stuff. It's all physics, what this engineering stuff is based on. Now, the electrical studies start with this law, Ohm's law. So what you got to do, and please listen to what I'm saying, because people don't listen, they do it another way, and they end up getting a bad grade in the course. One of the things you got to do to be able to solve problems in here is you got to be able to read the problem in words and then translate those words to a picture. The picture is called a circuit or schematic diagram. And so last class, I gave you some symbols for voltage. I gave you symbols for current. I gave you symbol for resistance. I'll put it on the board again today. But what you got to be able to do is you got to be able to read a problem statement and translate that problem statement into a picture called a schematic. And then what you'll do is you'll use that schematic to solve the problem. So what I want you to do for, just for the next few weeks is anytime you can draw a picture of a circuit, go ahead and do that and then solve the circuit from the picture. I want you to get used to it, because here's what happens. This is the first week we actually start the electrical stuff, and the circuits are going to be super easy. And you're going to be like, well, I ain't really got to draw a picture for that. I can just write out the equation, get the answer right away. And you're right, you can do that. What I want you to do is I want you to get used to drawing the picture while they're easy. Draw the pictures while they're easy, because here's what happens. We'll come in and we'll talk about Ohm's law this week. It's a piece of cake. We'll come in next week, we'll talk about series circuits. It's a piece of cake. We'll come in the next week, we'll talk about parallel circuits. Yes, it's a piece of cake, but then we take all that stuff, the series, the parallel, and we put it together into a more complex circuit, and guess what? It stops being a piece of cake. If you've already learned how to draw those and assemble those diagrams on paper and develop the right way to think about them, then we move to the more advanced stuff, the harder stuff. They say I shouldn't use the word hard when I'm teaching, but it's harder. It'll be a lot easier for you. The learning curve isn't that bad. But if you never ever drew a picture before of the circuit, and then you jump right into the more complicated stuff, that's when you get lost in the class. So always try to work the problem from the picture. So 99 times out of 100, I'll always draw a picture. If there's a time where I say, hey, you don't have to draw a picture for this, the equation says everything it needs to say, then you're okay. But for the most part, draw the circuit diagram, label your knowns and unknowns, and then solve the circuit diagram. And I'll show you examples of that today. So actually, we can do that right now. So I actually have I don't know if you have the topic sheet. If you don't have it, don't worry about it. I have it right here for you. Now, there's a way, if you go up to the upper left-hand corner of your screen, you'll see a little bitty box that if you mouse over it, you can actually zoom in on the document. And if you look at the document, I want you to go down to problem number 1, 2, and 3. These are practice problems for Ohm's law. So we're going to work these problems, but before you work the problem, what you got to do is remember what we talked about. Remember that when I want to represent a voltage, I have these specific symbols to represent voltage or a voltage source. A battery or any source of voltage can be represented like this, like this, or like this. Now we can use any one of these to represent a voltage source. Strictly speaking, this one and different. This one are different. This is called a battery, and this is called a cell. We'll learn the difference between those next week. This, however, can be either one of those. So if you want to represent a 12-volt voltage source, you draw one of these and you just put the value on it like that, or like this, or like that. So if I'm reading something and I say I have a 15-volt battery or 15-volt source, you're going to represent that with one of these. If I have a current, how do I show current? You're going to show current with an arrow. And I mentioned in the last class that when I show current, you put the amount right here, it might be 10 amps. There's two types of current. There's the actual current that flows in the circuit, which is called electron flow, or the reverse of that is called conventional current flow. I'm not going to go into that right now, but if you show a battery and you show current coming out of the positive terminal, then that's conventional current flow. If you show current coming out of the negative terminal, then that's electron flow. And I don't care which one you use, just be consistent throughout. Use the same thing throughout. I'm going to use this one. I'm going to assume current flows from positive to negative, even though I know it actually goes the other way. If I want to show a resistance, and this gets complicated, but right now we'll keep it simple. Any kind of opposition, I'm going to show with a symbol like this. And this means resistance. So I have symbols for voltage, I have symbols for current, I have symbols for resistance. Now, what if they give you something that you don't know what the symbol is? You don't know what the schematic symbol is. You have no idea. Then what you can do is, whatever device they give you, you can just draw a box. And you can label it. Most devices have two terminals, a positive terminal and a negative terminal. So if you draw a box, you just draw two wires coming out of it. And this might be a microwave. I don't know, a microwave. Well, I don't know what the electrical symbol is for a microwave. I don't even know if there's one. But I can represent the microwave in the schematic diagram by drawing a box with two wires coming out of it and labeling it microwave. And I can put it in the circuit. Another way to do this is to show everything as a resistance. So I might have a resistor. I'm going to call this R and then microwave. So I can represent anything as a resistor. There's always a way to represent it. So what you want to do is, on the problem, read the problem statement from the practice problems or homework or whatever you're doing. Read the problem. Read it a couple times until you understand what's being asked. Once you read the problem, you want to take that problem and turn it into a picture using these symbols. On the picture, on the diagram, write the values that you know and then write the value that you're looking for. And that picture should help you figure out which equation you're going to use. And then you use the equation and the picture to solve the problem. So I'm going to display the practice problems again. And I'd like for you to try on here problem number 1. So make sure you have pen and paper and a calculator. Read problem number 1, understand problem number 1, draw problem number 1, and then solve problem number 1. about one more minute, and I'm going to look at the problem. All right, problem number 1. It says you have a 100-volt battery that's connected to a 20,000 ohm resistor, and they want you to find the current. So what I did, I made a list what's given, a list what I'm looking for, and this list points me to the right equation I'm going to use to solve the problem. So I need I equals something, so I equals something is going to be that first one. Before I solve the problem, I wanted to translate it from words to a picture, a schematic. So I need a voltage source of 100 volts. I'm going to draw the voltage source. I have a resistance of 20,000 ohms. So I'm going to draw the resistor. Now, you guys should have coloring pencils. You should have rulers, straight edges. You'll be able to draw these schematics neatly. Anytime you have something in, it's got to be done in a way that I can read it, I can see it. It needs to be nice and neat. You want to color code values, and you'll see me do that as we go along. So I got my voltage source, 100. It says the resistance is 20,000. I'm not going to write it this way. The way you'll actually see that written on most documents is like this. And you should know how to get from this form to that form. So this resistance is 20 kilo ohms. And what I'm looking for is current. So I'm going to represent current with an arrow. And I don't know what it is, so I'll put a question mark above the arrow. So you'll show me that picture. Now I want to start with the working equation, the equation I'm going to use to solve the problem, which is this one. And the first thing I'm going to do is write the equation, not the answer, or not the equation with the numbers in it. I'm going to start with the equation I'm going to use to solve the problem. So I'm going to write this. I equals V over R. And then I'm going to put in my values for V and R. I'm going to substitute. V is 100 volts. R is, I'm going to put in 20K, not 20,000, 20K to make the math easy. 20K ohm. And now I can just cover that up, and I can say I got 100 on 20. Anybody can do that in their head. 100 on 20 is 5. If I have current, the unit for current is the amp, but I got 20 kilo ohms. Now remember what that is. 20 kilo ohms means that on the bottom here I have 1 over K, and the K is 10 to the third. So I really have this is really 1 over 10 to the third. And in math, you learn that if you have 1 over A raised to the n power, you can bring that up into the numerator by just taking the exponent and making it negative. So I can bring this up to the numerator by just taking the exponent and making it negative. And so that 10 to the third, when I do the math here, it becomes 10 to the minus third. You might remember that 10 to the minus third is a million. That's the lowercase m. So what you want to remember here as you do these problems is this. It's pretty simple. If I have 1 over K, if the K ohm is in the bottom, then when I do the division, it's going to come up as a million. If I have the milli in the bottom, it's going to come up as a K. So anytime you have K in the denominator, your answer will be in milli. Anytime you have milli in the denominator, your answer will be in K. If you remember that, then the math is super easy. I divide this. I have 100 on 20 is 5. Current has the units of amps, and so then I have K on the bottom, and K is going to come up as milli. This is 5 milliamps. So my answer is 5 milliamps. If this was a test or quiz, you want to show the working equation, substitute the numbers, and then circle or put a box around your final answer, and you're good to go. This current right here is 5 milliamps. Anybody have any questions over the first problem? Questions or comments? Okay, well, I'm going to share the document with you again. And this time I want you to do problem number 2. Problem number 2. Give you about 1 more minute, and then I want to go over this problem. 60 seconds. All right. Problem number 2. It says you have a relay. Relay operates on 48 volts and it draws 30 milliamps of current. What's the resistance of the relay? What is a relay? What's a relay? Where have you ever heard of a relay being used?
Relay race.
That's a good one. A relay is basically it's an electromechanical switch. You use a little bit of current to control a lot of current. A little current to control a lot of current. And there's actually a schematic symbol for a relay. But let's just say you didn't know what that schematic symbol looked like. How would you draw the circuit? Well, I got a voltage source of 48 volts. So I'm going to use one of my symbols for voltage. I don't know what the relay looks like, so I'm just going to make a box. And I'm going to label it relay. Now the other thing I could have did is I could have just made a resistor and call it R relay. And I can represent the relay because everything has resistance. Since everything has resistance, you can represent anything as a resistor. So I can do it this way, or I can just make a box and I can label it. I got a relay in these 48 volts. I have a current flowing into that relay, and that current is 30 milliamps. So I have a current. That current is 30 milliamps. I want to know how much resistance does that relay have. So I have my list here. I got V, I got I got R equals. I need R equals something. Well, R equals is this one. I'm going to use the last form of Ohm's law to solve it. I'm going to first write my equation. R is V on I. I'll make my substitutions. V is 48. And I is 30 milliamps. Now I'm not going to write the 30 as 0.03. I'm going to write it as 30. I got 30 milliamps. And what I'm going to do to get the answer is I'm going to divide 48 by 30. What's 48 divided by 30? How much is that? 1 point what?
6.
1.6. I know I'm talking about resistance, so the unit has to be omega or ohms. And remember, I have 1 over m. If I have 1 over k, it comes up as a milli. If I have 1 over milli, it comes up as a k. Since that's 1 over m, this is going to be k. It's 1.6 k ohms, or I can write it as 1,600 ohms. Either way. So anytime I'm using that replacement for 10 to the minus third or 10 to the third, or whatever the engineering notation gives us, I leave it in that notation. Just kind of know what you're dealing with, and you know what you get. You know you have 10 to the minus third on the bottom. You divide is going to come up as a k. You know, you have K on the bottom, 10 to the third, means the value is going to come up as 10 to the minus third. So there are 3 examples of applying Ohm's law. And this is, I mean, who can't do this? This is simple. But what you want to get used to doing is reading a problem, a word problem, abstracting from it, and coming up with the circuit you're going to use to solve that problem. This is nothing here. This is a piece of cake. But as we go through the course, the circuits will become increasingly more difficult. So while it's easy now, get used to doing it this way. And as we introduce other symbols and other ideas, you'll be able to follow it. Okay? Anybody have any questions or comments on Ohm's law? All right. Well, the next topic I want to talk about is something called power. Power. So we got voltage. Well, voltage is just a separation of charge. We got current. Current is charge in motion. We got resistance. Resistance is opposition to current flow. And now we got this thing called power. What is power? What is power?
How much voltage the battery gives off?
Somebody said, how much voltage the battery gets off? Okay. Well, that's one idea for power. Anybody else have a different idea?
How much current you receive?
Okay. Both of you are partially right. One person said how much voltage you have or the battery gives off, and the other one how much current something receives. It's actually a combination of the two. What you're doing is you're delivering energy from the battery to some device, from a battery to a light bulb, from a battery to whatever, a motor, right? And the way you're doing that is by pushing electrons along the wire, giving those electrons energy, kinetic energy. So the current kind of relates to the kinetic energy, and the voltage kind of relates to the force of the push of the electrons. So there's a little bit of V and a little bit of I. Let me give you a strict definition for power. It's actually 2 of them, depending on how you want to think about it. So write this down. I don't know if you guys are taking notes or if you're just going back watching the videos, but you really should do both. You want to make sure you take notes and you want to make sure you review the videos. So take notes. Power. 2 definitions for power. You can think of power is a rate of doing work. Rate of doing work. It's a rate. What does that mean when I say rate? What do you think about when I say rate?
A quantity or amount?
Yeah, but give me more. It's deeper than that. It's deeper than quantity or amount. What's a rate? What do you think of?
Like
How
overtime?
much you work in a time over time?
Yeah. It has something to do with time. A rate is how fast. If you do something at a high rate, that means you're really fast. You do it at a slow rate, well, you're really slow. The rate has something to do with something happening fast or slow. And somebody mentioned time. In physics, we have time rates. We always look at how quickly something happens in a certain amount of time. How much work can you get done in 8 hours? That's a time rate. How much money can you make in 1 day? That's a time rate. In physics and business and so many, we deal with time, so we have time rates of change, right? So I might say, I drive 100 miles in 2 hours. Well, my rate is 50 miles per hour. We call that the speed. Time rates are big. So power is a rate of doing work in a certain amount of time. Let me give you an example. Let's say you got 2 electric motors. I got motor A and I got motor B. Motor A has a power of 5 horsepower. Motor B has a power of 10 horsepower. Now, I don't know what the shaft is driving, but when you turn these on, the shaft spins. Maybe it's driving a pulley system. I don't know what, it's driving something. But motor A is 5 horsepower, and motor B, this power is 10 horsepower. What's that mean? Well, it means in a given amount of time, motor B can do what? It can do twice as much work as motor A. So how much work can I do in a certain amount of time? Power is a rate of doing work. The higher the power, the more work you can do in a given amount of time. This can do double the work than this one. So one way to think of power is a rate of doing work. And this word rate, by definition, means that in the equation, you're going to have time in the denominator, T-I-M-E, time. The second way of thinking about power is this. Again, it's a rate. It's a rate. It's a rate of converting energy from one form to another. It's a rate of converting energy from one form to another. Well, what the heck does that mean? A rate of converting energy. Well, let me give you an example. Now, you guys, you probably don't. When I was a kid, cars weren't as complicated as they are now. And when I turned 16 and started to drive, back in those days, you can actually take an automobile and take your radio out and go. There used to be a store called Radio Shack or Circuit City. You can actually go to a store and buy a radio for your car and install it yourself. It wasn't that difficult. You can put in the speakers and amplifiers. We got into all that. Now you guys, all you do is sit around on your phones and text, and everything's virtual and online. So you probably don't do any of that stuff. But back in the day, you could do that. And you can buy a speaker. I might have a speaker. And that speaker might be 100 watts. That's the power of the speaker. And so what the speaker does is the speaker takes in electricity or electrical energy, and it converts it to something else. It converts it to sound. This speaker converts energy from one, I think I spelled electrical wrong, but you get it. It converts energy. Well, this is going on YouTube. I got to straighten this out. I don't want the YouTube people to think I can't spell anything. This is electric. You guys know you're on YouTube, right? So if you have your camera on, and they're all public, so anybody can watch the videos. Anybody who wants to learn can watch the videos, but they won't get a grade unless they pay. You got to pay since the next day to get a grade. But the speaker converts electrical energy to sound energy, acoustical energy, or mechanical energy. It converts energy from one form to another. So the rate at which it does that is another way to think about power. So there's two ways I can write the formula for power. Remember, it's a rate, so I got to have T in the denominator. So I can write it like this. I can say power is work done per unit time, or I can say power is energy converted over time. I can write it either way. If I write it this way, and I can abbreviate it, I can say power equals, for work, we'll have capital W per unit time. That would be the formula for the first way of thinking about power. And for this way, it'll be power equals E for energy per unit time. And notice I got the T in the denominator. Like I said, in physics, this is called a rate or time rate of change. And that's what these are. Now, what is the unit? What's the unit for energy? Anybody? What's the unit for energy?
Is it the watt?
Is it joule?
It's the joule. The energy is the unit for energy is the joule. And of course, for time, it's the second. So power has units of joules per second. What about work? What's the unit for work? Well, in the last video, you learned that work and energy have the same unit, joules. So the unit for this is the joule. The unit for this is the second. So power has units of joules per second. Joules per second. And what we do is this. Somebody said this is the watt. Well, just like for voltage, we said voltage has units of joules per coulomb. 1 joule per coulomb, we call that 1 volt. Or current has the units of coulombs per second. 1 coulomb per second, we call that 1 amp. If I have a joule per second, 1 joule per second means I have 1 watt. So we use watts for electrical power, and we use a capital W to represent watts. So I might have a power of, something has power of, let's say 13 joules per second. That means the power is 13 watts. It says that's capital, that means it's named after somebody. Remember, if the unit is capitalized, it's named after a person. This person's name is James Watts. James Watts was, of course, a physicist. Okay, well, that's kind of nice. I get that. This is new. It's cool and all that. But we got one problem. I'm looking around the lab right now, and I see equipment. I see a meter that can measure voltage. I see a meter that can measure current. I see a meter that can measure resistance. But I don't see a meter that can measure energy. I don't see a meter that can measure work. There's no way to measure it. So it'd be nice to figure out a way to get the power using the big three. It would be nice to get the power using voltage, current, and resistance, or some combination of those. Is it possible to calculate power not knowing the energy or not knowing the work and the time? And the answer is yes, if we use something called Watt's law. Watt's law. Let's look at Watt's law. Watt's law says that you can get the power if you take the product of voltage and current, and your units would be in watts. P equals V times I. Now let's see if that makes sense. What are the units for volts? A volt is equal to a joule coulomb. 1 volt is 1 joule per coulomb. And we're taking that V and multiplying by I, so what are the units for I? Well, current is in coulombs per second. So the question really is, what do I get if I take a joule coulomb and I multiply it by coulomb second? And what happens is, it crosses out, the C's cross out. So what this thing on the left ends up having the units of is joules per second, and that's exactly what we want, because we said a joule per second is a watt. So that's kind of nice that God arranged it so, or somebody arranged it so that if I take the product of V and I get the thing I want, power, in watts. So in Watt's law, we can calculate power by the product of V and I. Now, we got about 3 minutes, so I think I got enough time to do this. Here's what you can do, though. If you wanted to, you can take this equation and mix it up with Ohm's law. You can do some substitutions on V. You can do a substitution on I to get a different equation that might be useful. So, for example, instead of taking P equals V times I, what if I take P equals what V is equal to times I? What is V equal to? Well, V is equal to this. So I'm going to take the V and substitute for the V what it's equal to. V is equal to I times R. So this V is really I times R, and I'm multiplying that V by I. If I do that, then what I end up with, I times I is I squared R. That also gives me P. So now I don't have to just use this one right here. I got another way to get the power. I can take P as V times I, or I can say that P is I squared R. That's the second form of Watt's law. And then finally, you might think to yourself, well, I don't want to do that. I don't want to substitute for V. Same thing, what I want to do is substitute for I. What would that look like if I substitute for I? What would that give me? Well, if I substitute for I got P equals V times I. So I got V times I. I'm going to multiply that V not by I. I'm going to multiply by what I is equal to. What's I equal to? Well, Ohm's law says that I is equal to V over R. So in the place of I, I'm going to substitute what it's equal to. It's equal to V over R. So now I got V times V over R, and that's going to give me V squared over R. So P is also equal to V squared over R. So now I got a third way of calculating power. P equals V squared over R. And now, no matter which two quantities of the big three I'm given, the voltage, current, and resistance, no matter which of the two I'm given, I can always find the third. I can always find power. So I got P is V times I, P is I squared R, and P is V squared over R. And guys, what you're looking at right now are the 6 equations that you're going to use for the whole semester to solve almost every problem. The only thing I'm not showing here, there's 2 laws we got to talk about, and that's it. With these 6 equations and the 2 laws I'm going to talk about, you can solve a DC circuit problem that I could give you. So this is almost everything. Okay, so we talked about power. We introduced you to Watt's law, and we derived some other forms of Watt's law. And so now what we want to do next class is we want to practice using Watt's law on some problems. And then I want to talk about something called efficiency and calculate the cost of energy. So that's kind of what's coming. But we're out of time now. So guys, thank you. I'm a minute over. So thank you for hanging in there with me. Before I sign off, I want to ask, does anybody have any questions or comments for me? Questions or comments?
So for homeworks that we run in lab, is it only homework 1 and supplementary quiz, or do we have to turn in the practice problem too?
Yeah. So what you're going to turn, and I'll put this on Blackboard. I've only given you 1 homework assignment. I gave you chapter 1 homework assignment. Chapter 2 is more physics stuff. I didn't really want to give you homework for that. Instead, I gave you a supplementary quiz. That's something you're going to turn in. So you'll turn in homework 1. You're going to hand that in to me on Tuesday. You'll turn in the supplementary quiz. You'll hand that in to me on Tuesday. You should have already did the labs. All the labs have been something that you upload to Blackboard. So that should have been already done. The universe assignment, that was an extra credit type thing. That's something you upload to Blackboard. That should be already done. And I can't remember if there's anything else, but anything you need to bring into me on Tuesday, I'll have a list of that for you. You bring it in on Tuesday. As far as homework for this, what we're talking about now, we're actually covering 2 chapters. What I went through now is in chapter 3, and what I'm going to talk about, Ohm's law is in chapter 3, and power and energy, which we'll talk about on Friday, that's chapter 4. So we're taking 2 chapters together. So in the next couple of days, what I'll do is I'll pick up some problems I want you to do for homework. And I think I'm going to do the same thing I did with homework 1. I don't know if everybody has a book yet or not. I'll just make copies or maybe assign it off the the book. Did I give you guys a link to the ebook that I have?
Yeah,
I don't
you
know if I
put
gave
it,
you-
you put it on announcements.
Yes. If you have the link to that, I'll just assign problems out of that, and you'll know what they are. Those will not be due on Tuesday. I want to give you more time to work on them. So chapter 1 assignment will be due. You got chapter 1, you got homework 1. I can't think what else that's a hard copy. I think it's just those 2. It's on Blackboard though, and what I will do is I'll make a list. It'll be crystal clear what was due, what should have been uploaded already. I'll make a list and it'll be clear. Okay? Anybody else?
Did you get my question on text about the lab?
I did not. What was your question?
So I use like an iPad as a laptop, and the labs were not working there. So I was going to.
Oh yeah. Okay, yeah. I think I saw that text about 4 a.m. this morning or something. I think I did see that text. Yeah. Well, do you have a machine that they'll work on now?
Yeah.
Okay. Go ahead and perform the lab if you haven't already done it. And I don't want you to email it to me. That's not a good way to turn anything in. Go ahead and do the lab, and when you get it done, send me a text. I'll respond to you, and I'll just have to unlock the website, unlock the link so you can upload it to Blackboard. I'll have to do it that way.
All right. Thank you.
Okay? You're welcome. Anybody else? Is that Spencer? Spencer, your hair, you need a haircut. Your hair grew since last time.
I know. I'm growing it out for a while.
You've been locked down for COVID. I don't have that problem. I don't have any hair, but you guys can't get to the barbershop. Man, I can take some of your hair and I can use some of that on my head. Okay, guys, have a great one. Stay safe. I will see you on Friday.
Yep, see you Friday.
Thank you.